first part of the talk, which is just talking about what's the current knowledge, which is changing day to day almost, on why our Gulf of Maine water is warming up so fast. So, you remember this from grade school, our Earth warms up because sun comes in through the atmosphere. Some of it's deflected by clouds and snow, and some of it's absorbed in the atmosphere, but 1.10 times the 17th watts reaches the land, sea, and atmosphere. And some of that is radiated out. Fun fact, light bulbs don't just keep getting hotter and hotter until they explode. They actually reach an equilibrium based on how much energy they're receiving and how much light they give out. The same for the Earth. Earth is not getting hotter and hotter and hotter. It has reached an equilibrium close to 15 degrees Celsius, and we radiate out infrared light versus visible light. The problem with greenhouse gases, as we know, is it's absorbing more of that heat and radiation. Of course, latitude plays an effect in looking at how much sunlight and how much insolation we receive on the planet. At a low angle, you're going to have less sunlight coming in. Sunlight strikes directly at the equator, where the most amount of influx of heat comes in. More heat leaves the poles than leaves the equator, so the poles, of course, are colder. So except for ice ages and recently the climate change and global warming, the temperature of the Earth has remained relatively stable over millennia. The reason for that is there's tons of different transport mechanisms, which I'll talk about. And what we're going to talk about with the Gulf of Maine is something that scientists didn't even predict 100, 200 years ago, is changes in these transport mechanisms. And that's what's so not necessarily alarming, but interesting about what we're seeing. So of course, we all know about the greenhouse effect. Of course, when I was a kid, we didn't talk about this because we didn't really know about it. But over time, we know that we're introducing way too much CO2, methane, and other gases into the atmosphere, and that is trapping in heat. And our entire planet is warming up. We see that in sea surface temperatures, land temperatures. We see that in changes in biodiversity, and we can measure it in the atmosphere. So there's three ways to transport all this heat that we're introducing. There's through winds, there's through the currents that the winds create, and there's through thermohaline circulation. And the main thing we're talking about today is thermohaline circulation, named after thermo for temperature, haline for salinity or salt. So when ice forms at the poles, it creates this brine of saltier, denser water underneath it. Fresh water is what freezes out of salt water first. In fact, if you were ever floating around at the North Pole and need to drink anything, you can totally drink the ice. Same on Nantucket or anywhere else. The salt water underneath it is something you don't want to drink. This water freezes at a lower temperature too. It changes the freezing temperature. So it's super cold beneath it. So it's going to add to the density. It's going to be cold and it's going to freeze and sink. So where sea ice is being actively formed, it's going to be denser. It's going to be saltier and it's going to be colder and it's going to sink all the way to the sea floor. It's going to fill up all of these basins and start flowing around the planet.
That's how we do it.
Here's exactly what it looks like. Oops. Bad. So we've got warm and fresh water is less dense. Simple density experiment. With kids, I'll do this with you. They can see that warm, fresh water is less dense. Cold, salty water is more dense. So if the Bering Strait wasn't so shallow, it would flow backwards and around on that side. But because it's really shallow, it acts as a dam. So almost all the cold water that's forming over by Nova Scotia, by Greenland, it's going to flow through two locations. Through the Greenland and Iceland opening and between Iceland and Norway. And it's going to mix with some of the cold surface water in the shallow parts of the Arctic. And it's going to form something called North Atlantic deep water. Same thing happens in Antarctica in the Weddell and Ross seas. Cold, really salty water is created. It mixes with a little bit of surface water from all of the ice that's freezing out there. And because it's not impeded by any kind of a sill, it flows into the major oceans as the Antarctic bottom water, AABW. The Antarctic bottom water is a little denser than the North Atlantic deep water, so when they meet, it's going to flow underneath that. And this is basically what this looks like. There's the surface water there at the equator. We've got Antarctic water, North Atlantic deep water here. So this is the North Pole, the South Pole is the left. So your North Atlantic deep water is going to flow over that Antarctic bottom water. You've got Antarctic intermediate water that's also created that's forming a wedge right there. Here's another version of this, a thermohaline circulation, once again, Oceanography 101, showing your surface water stretching all the way out here further north and this intermediate water, which is actually pushing some of that surface water, your North Atlantic deep water and your Antarctic bottom water. Now, all of this pushing and shoving between hot and cold water is going to start setting up these gyres. So this is how everything gets connected. All this cold and warm water is going to start circulating around the globe. Anywhere that cold water flows out, warm water something has to flow in. And typically it's warm water that comes in and fills in those spots. And so you set up these big giant gyres as a part of the Coriolis effect, centripetal and centrifugal force are going to steer your currents and create these giant gyres. This is going to balance the entire Earth's heat budget by moving heat away from the equator and up to the poles and vice versa. So this keeps circulating over and over again. Wally Brooker developed the idea of a global conveyor belt just in the 70s. This is all, for people my age, relatively recent, connecting the circulation of the globe before we really didn't know how all of this connected. He used a series of dating techniques to actually date the currents as they moved using tritium and carbon-14. So we could see how old these currents were, especially at the seafloor. And he developed the global ocean conveyor circulation, releasing heat up at the poles, transporting heat around to everywhere it's warm. You can see these arrows going through here showing exactly the movement is all connected. I actually got to meet Wally Brooker. He is technically grandfather in science, my advisor. He was the advisor for my advisor. So I got to meet him at Vermont Dower. He's really got a couple of books that he wrote on tracers in the sea in my office. And he was one of the first scientists to predict global warming and to attribute it specifically to CO2 buildup in the atmosphere. Way before Wally Brooker was Benjamin Franklin. Benjamin Franklin was the first person to chart the Gulf Stream. He discovered when he talked to Timothy Folger, a whaling captain, that Folger could make it over to Europe much faster than other British whaling captains. And that's because Timothy Folger, and many whaling captains knew about the Gulf Stream and used it as a conveyor belt because it would actually pick them up and move them along. But he also knew if he came across the to avoid it so that you're not going against a really high, strong current. So Franklin learned about this in order to speed up the mail. This is a slide of the general circulation here in the Gulf of Maine. The Scotian shelf will come back to all of this. The northeast peak, this opening right here, George's Bank, which has this great circulation there that keeps nutrients there in a relatively shallow area in the photic zone. Here's another picture talking about regional circulation. So we'll be talking about the Labrador Current and the Gulf Stream. And what's happening is changes in the Gulf Stream and weakening of the Labrador Current and a weakening of this are shoving more hot water up into the Gulf of Maine. Here's another illustration of some of the currents and motion around George's Bank and around the Gulf of Maine. Anytime you have a current going one way, you typically get a counter current going the other way. And so you'll have opposite currents. Those form shear boundaries where, as you know, a lot of things happen with phytoplankton. Mixing of waters, you end up having more variability and dynamics coming off of that. All of this has been changing over the last 100 to 200 years and drastically lately. Here's what the Gulf Stream looks like. If you look at a whole decadal change, it oscillates quite a bit. I kind of illustrate that it's similar to holding an eel. It's not like the same thing. It tends to flop around quite a bit, move. It generates these cold rings that come off of here. I'm going to show you a couple of animations that show that. And it's also going to fling off warm core rings. So those are rings of cold and warm water that are flung right off the Gulf Stream. This happens also over the Kirishio Current off of Japan. So it's not just for us. This is for any of the large basins on the east coast of the western coast of large basins. So you can see these warm core rings starting to form and spin off, and cold core rings forming. So that is the movement of the Gulf Stream with that very cold air water coming down from the Labrador Current. This is in 2018 in April. Snapshot from yesterday. And if you guys recall that there's a lot more cold water coming down here because it's February. So we've got a large amount of cold water there. This is the sea surface height Chart, the last one was the sea surface temperature. Warmer water is actually higher on the surface of the planet. And so now they often satellites will look at sea surface height in order to indicate where the Gulf Stream is. And so you can see that the Gulf Stream is actually piling up right there. And these are cold pockets south of there. Warm water poisons expansive. So it's getting hotter. Just last week on February 15th, the Gulf of Maine Research Institute released a really important paper talking about 2022 being the second warmest year ever recorded for the Gulf of Maine in the time that they've been recording. They found that the Gulf of Maine is warming faster than 97% of the rest of the world's oceans, and in fact was 53.66 degrees Fahrenheit, which is really hot, about 4 degrees above the long-term average, and about half a degree below the record set in 2021. Here are all those years stacked up. Here's 2022. Here's the very hottest year at the very top, which is 2021. You can see that all these years fall within the last couple of decades, getting warmer every year. We can also see this top line is the increase in temperature for the Gulf of Maine, and this is for the world's oceans. Of course, this is a problem for us, an existential problem for us to have all this hot water piling into the ocean. Here is a average temperature anomaly. So this is based off of the average. So everything in the red is a warmer temperature than you would normally find. I think the time period they used to base the anomalies on this is 82 to 2011. And that is getting warmer and warmer with even more water here off the Scotian shelf, right here, than in the Gulf of Maine itself. So another picture showing the world's temperature anomalies. And one thing that's important when you're talking to people about global warming is showing the entire sea surface temperature and global temperature. This was 2022 was a La Nina year, so you can see that effect right there. There's colder, and with all the ice melting, we're actually getting much colder at the very top. So we do have some cold areas, but you see a lot of red on there too, which shows average temperature anomalies. And you can see, though it's kind of tiny, at the very top right here, you can see the Gulf Stream. I don't think you can see this, but yeah, right there, you can see the Gulf Stream, how much hotter it is right there. It's actually piling up, and that's one of the problems that we're having is it's getting backed up there because the Labrador current is changing too. One of the things they've been talking about in the last few years is this new term called a marine heat wave. And it's a time when there are 5 more consecutive days when sea surface temperature is greater than the 90th percentile of the longest term average for that day. And if there's a gap of 2 days, then that's not counted as a gap. But you can see this is recording marine heat waves over several years. And we're having way more heat waves now than before. So this is 2020, 2010, 2000s to the 90s. That's scary. That's a lot of heat. On the left is showing how much of 2022 is experiencing a heat wave. And there are only 2 little tiny divots where it was below normal. 97% of the year, it was inside of a heat wave. So that forcing is not only, if it was something that was just episodic, occasionally happening, creatures could evolve, we could evolve, but this is becoming a permanent situation. So why is this? Mainly it's a problem with the Labrador current in the Gulf Stream with some atmospheric forcing going in. So the Gulf Stream is going further and further north, mainly as a result of the weakening Atlantic Vertical Overturning Circulation, or AMOC, which is those ocean currents that I showed you earlier, that Atlantic portion is the AMOC, the surface part of the ocean conveyor belt. So the Gulf Stream is just the surface part of the AMOC of the North Atlantic. And climate models suggest that the AMOC will weaken over the 21st century as greenhouse gases increase. This is because as the atmosphere is warming up, the surface oceans beneath it are retaining more heat. Meanwhile, increases in rainfall and ice melt mean it's getting fresher. So all these changes are changing those density differentials and changing how much water is sinking and slowing down the whole ocean conveyor belt. At one time, they even thought that the Gulf Stream could shut off all completely. This is affecting like the heat waves that you might have noticed in Europe a couple of years ago, those giant heat waves where no one has any air conditioning. That's because they never needed one until now. They're going to need it a lot. So there's 2 primary causes for this unusual warming. One is the greenhouse gas concentrations going up, Second is that melting of ice in Greenland and the Arctic Ocean, which is providing these pulses of fresh water which are changing the density. This weakening is leading to the Gulf Stream shifting northward. And the cold current flowing into the Gulf of Maine becoming weaker, pushing warmer water up into that region. We're seeing that with all kinds of creatures. So, on the day after tomorrow, they have this overnight ice age. That's not going to happen. But there's a few things that they did get right, including the fact that more ice is melting and the North Atlantic is getting less salty. That part of the day after tomorrow is correct. Not much else is, and it's not the world's greatest acting, but it's better known. Here is that sea height measurement that I was talking to you before that's showing the Gulf Stream piling up here. You can see it right inside this box. See that dark red? This is sea surface height now, not temperature. So the blue is lower height and the red is higher height. So it's literally piling up there because it's not continuing over here to Europe. So it's getting pushed up and toward the Gulf of Maine. All of these are a series of different simulations or proxies for things like coral, measurements of sea surface temperature, and a variety of different pockets. So this is global sea surface temperature, terrestrial proxies, sortable field data. So this is all a series of different experiments that all show that AMOC weakening, that Atlantic meridional circulation current weakening and weakening. This shows how much it's accelerating. So it was going up. This is from, you guys discussed this a couple of years ago, this is a recent paper. And you can see that this trend is accelerating in both cases, both in summer and year round. Summer, winter, and year round. It typically is actually greater in winter. You guys are all familiar with this, but one of the reasons I included this is just to show the tail of the Grand Banks and to show some of the bathymetry that has something to do with it. So changes we're seeing in the Gulf Stream that are preceding all this warming are actually changing some of the circulation and jamming some of that heat up into these openings. These gyres are physically changing based on changes in the Labrador current and the Gulf Stream. The Gulf Stream is getting more and more further north, pushing the Labrador current back and out. That's all the satellite altimetry. The Brickman paper you all talked about shows that opening into this passage here and how that's actually shoving some water in here, changing some of the small gyres too in this system. So because of the bathymetry and because of these openings, the tail of the Grand Bank is really providing a big access point. And last but not least, there's also some small amounts of atmospheric influences. You've been recalling about the big changes in the polar vortex and then the jet stream. Lately, we're seeing the jet stream actually stay up further north. We've had an unusually warm year this year. Part of that is because the jet stream is not dipping down as much and it's not oscillating as much as it used to. This is from one paper where they looked at buoy information in many, many locations, and they showed really high temperatures at all the buoys, showing that there was some atmospheric component. This is the only person that's found an atmospheric component so far. And I'm all done.
So I'm going to pick up where Sarah left off here and talk a little bit about the anticipated impacts of this warming on the Gulf of Maine, and as kind of a framework for discussion of some of the anticipated changes in the Gulf in terms of its effect on socio-ecological systems, on the humans that live around the Gulf of Maine, as well as the animals that live within it. I'm going to go back in time a little bit to 2019 and I'm going to talk about a gathering that we had. It seems like forever ago, pre-COVID in November 2019. This was a meeting called the Gulf of Maine 2050 Symposium that we held up in Portland, Maine. And the reason it was Gulf of Maine 2050 is the year 2050 is when a lot of the global climate models are expected to really start to diverge in their trajectories, depending on what actions we take to mitigate carbon emissions. So with that, I'm going to talk a little bit about the approach that we took leading up to that meeting in terms of considering, first of all, what's happening within the Gulf of Maine, but in turn, the effects it's going to have on communities. We have our advancing keys here.
You had some trouble with that. I had to use the keys right there on the Zoom. I'm sorry, right by the mouse pad.
There we go. Great, thank you. So ahead of the Gulf of Maine 2050 conference, we gathered together several working groups to focus on different aspects of change in the Gulf. Those included ocean acidification, as well as ocean warming and changes in circulation. So this was a very interdisciplinary approach of a group of scientists from all different backgrounds and organizations working around the Gulf of Maine. And so ahead of that 2050 conference, we gathered and started to consider, first of all, the hydrologic modeling component, which I'll talk about a little bit, but then also in a very interdisciplinary way, the effects of the warming that Sarah talked about within the Gulf of Maine. So first of all, there's a whole modeling exercise, and Sarah presented some of this work earlier on in the talk. There's a series of modeling exercises done by the team of folks whose expertise that is. And, one of the biggest challenges with this kind of work is sort of downscaling from the global climate change models to more local and regional oceanography. But the team put together a series of models and was able to project some temperature change outcomes, some of which Sarah touched on. And from that effort, this is where kind of folks like me get involved, where I'm very much a generalist. I'm not an oceanographer, but I know a little bit about oceanography. We had experts on a variety of different marine species, seabirds, whales, fish, invertebrates. And so we gathered together to consider the effects of the modeled warming on the Gulf on these different species. And the way we consider that, the reason we did that, we tend to focus on species that we know respond, and in terms of when and where they go, they shift their distribution in response to temperature changes. So we focus on a variety of species, some of which I'll touch on in more detail, like right whales, squid, black sea bass. These are species that are documented to have distributional responses to warming temperatures. So they shift when and where they go, when and where they migrate, and things like that. The other thing to consider is changes in dynamics of invasive species and diseases. So we know that with warming water temperatures, we see increases in things like invasive tunicates, green crabs, which can have a particularly devastating effect on things like soft-shell clams, fragile eelgrass habitats. We know that warming water temperature affects disease dynamics in oysters. If anyone here is an oyster harvester, that temperature is really important when it comes to potential for bacterial contamination and disease. We also considered changes in the timing of seasonal events or phenology, and this is from some work the center's Christy Hudak and I worked on as part of a very large collaborative effort led by my friend Michelle Stoudinger. We looked at the changes in seasonal timing of migration of a lot of different species and other seasonal processes. And the big concern here is that as water temperature warms and as these patterns of migrations and distribution of the when and the where change, you can have decoupling between things like seasonal abundance of plankton and the predators that eat that plankton, seabirds and the small fish that they use to feed their chicks. This can have really dramatic effects on populations, reproduction and recruitment of populations and things like that. And, just to give an example, when we think about when and where animals go and the direct impact it can have on our livelihoods, particularly when you think of commercial fisheries, that's kind of the arena that I work in, as we look at the projected changes in distribution of species, this can have a dramatic implication for not only fisheries in terms of the folks that harvest them, but the way we traditionally manage them. If you look at this figure here, you're looking at projected shifts in distribution of summer flounder or fleet on the left, and Atlantic cod to the right. And you can see that the red means they're going to be increasing in the Gulf of Maine. They're projected to increase in biomass in and around the Gulf of Maine. And you can see the summer flounder are typically a southern species, and they're managed as a southern species, but they're becoming more and more abundant in the southern Gulf of Maine around Georges Bank and within the waters of the Gulf itself. You can see that cod in turn are likely to become less abundant. And these things can be due to direct physiological effects. Animals perform best at certain temperature ranges, and I'll touch on that as well. But also it can affect survival of larvae. If there's no food for the larvae because of changes in abundance of their prey or outright thermal stress on the larvae, these fish won't make it to adulthood. That process called recruitment. So I'll touch on that in a little more detail, but just to give you a sense, these are two commercially important species. Fluke are typically more important and are managed to the south of where we are here in the Cape, and within the Gulf of Maine. Atlantic cod is typically considered a Gulf of Maine species and managed accordingly. But as these animals shift in distribution, not only is that having economic effects on fishermen who can no longer access those resources, but it also affects how we manage them, how we allocate quota and things like that. So there's an enormous amount of complexity in terms of the socio-ecological system, not just the ecology itself, but thinking about how we interact with those species as we harvest them, as we try to manage those harvests. Of course, thinking in a little bit more detail now, we've talked a little bit about some of these things, but changes in productivity, changes in community composition, ecosystem services, all of these things are predicted to happen with changes in temperature. And that in turn has dramatic implications for when and where we do things as a species. It does have implications for our traditional coastal activities, and whether that be fishing or ecotourism or whatever it is, as animals shift their distribution, as the system responds, it can have really dramatic impacts on our economy and on our culture. So very much remember to consider humans as part of the system as well. So to circle back a little bit to that approach that we took to trying to consider the effects of warming on the Gulf of Maine, basically what we did, these are not sort of quantitative predictions so much as considering everything we think we know about the animals that I'm going to talk about, making some inference based on some model projections, as well as our general natural history, published associations between distribution and water temperature and things like that. So this is an increasingly common approach in this kind of field where you assemble a team of experts from all different disciplines. We do our best to consider the potential effects of things like warming waters. And so this is a very crude schematic, but it gives you a sense of, basically our state of knowledge of what was going on in the Gulf of Maine. Remember, this is the Gulf of Maine centered figure here. You're thinking about a few different species within the Gulf of Maine in 1985, 2015, and then projected forward to closer to 2050. This is taking into account, again, a variety of different things that we think we know about the populations of these different animals. And I'll get into a little bit more detail about some of these specific species. But you'll notice, for example, the appearance of a couple species in 2015 that you don't see in this figure in 1985. I'll talk a little bit more about squid and black sea bass. You'll notice as we get closer to 2050, North Atlantic right whales moving potentially more out of the Gulf of Maine, and that's in part due to a change in the abundance of their copepod prey. So I'll touch on a couple of these in a little bit more detail here, but again, this sort of multidisciplinary approach, trying to consider everything we know about these animals in a very holistic way. Can't give a presentation these days without at least touching on the North Atlantic right whale. This is from some work by colleagues of ours, but that incorporates a lot of data that we collect here at the Center for Coastal Studies, looking at distribution of right whales, looking at their zooplankton prey. In this room right now, there's folks a lot more qualified to talk about this than me, so feel free to correct me. But this is basically, if you look at the figure on the right-hand side, looking at shifts in distribution of right whales over the last few decades. So if you look at the top panel there, as the Gulf Stream is a little further south, and it's a grossly simplified version of what Sarah was talking about earlier. But you can see, the North Atlantic right whales were predominantly concentrated in foraging areas around the Gulf of Maine. But if you get to the more recent decade, we saw a shift in distribution in ocean currents, in the zooplankton, particularly the copepods, Calamus marchicus, that North Atlantic right whales eat, as well as other species, shifting to the north, places like the Gulf of St. Lawrence. And with that, again, thinking back to the consequences of changing distributions, in this case, it moved right whales to areas where at the time they were managed very differently in terms of the effects of humans on the species. So in places where there was a lot more, less regulated ship traffic, potential for interactions with fisheries that are managed in a different way than we do here, and that in turn led to a significant mortality of Atlantic right whales, arguably pushing them a little bit closer to extinction based on the distributional shift. So these kinds of changes can have really dramatic impacts. I might toss this slide, but I rolled this in there just to show how the data that we collect here at the center and other organizations, we're responsible for a lot of these dots down here to the southern. is used to look at shifts in distribution at a broader scale throughout the species range here, at least in the northern part of its range. Shifting gears a little bit and thinking about a different species, in this case concerning American lobster. Now this is a species that's really economically important for us here. It's one of the more socioeconomically important species for our fisheries in the region, culturally important. And so studied fairly extensively. In this case, we actually have some projections of what recruitment for the species is going to look like over the coming years. That's based on some historical data. So when I say recruitment, I mean the transition from an egg to a surviving lobster, essentially. In that early year of life is a time when these animals are very vulnerable to things like thermal stress, predation, all of these different things. And temperature is going to go down a really dramatic impact on the very early life history of these lobsters. And if you look at the bottom left there, that's a young of the year American lobster. We sampled in Pleasant Bay, the eastern shore of the Cape. And it's really tough for these animals to make it to that size. Their survival increases once they're of that size, but so this modeling work that Arno did is based on predicted changes, effects on of water temperature on that early life history, that survival to that young of the year size. And we measure this by doing things like setting cages or benthic collectors down the bottom and collecting the newly settled larvae over the course of the season. And that's work that's indicated over time that recruitment seems to be shifting. And so if you look here, we've seen some changes in survival and recruitment from the 1990s up till more recently here. We've seen a shift in the distribution of that survival, these lobsters. And then if you look ahead, given something that we know about warming waters, we're really seeing a decline in potential survival of these little juvenile lobsters in the southern Gulf of Maine around Cape Cod. If warming continues at its projected rate. And, obviously that's of great concern, and we're already seeing some hints of that in the way we measure survival of these little lobsters. We have seen a decline in many areas of these little young of the year lobsters. So we're right now working with the state of Massachusetts and other groups to consider how to expand our surveys to see if we're missing those little tiny lobsters, if they're simply shifting in distribution, or if they're really less than them overall. So stay tuned on that. And some of you may have also heard we're doing some work looking at seasonal hypoxia in Cape Cod Bay and how that affects adult lobsters and when and where they go, as well as mortality. So and there's some linkages to suggest that in turn is also driven by regional warming. So more of those stories, but that's an example of a really important species in terms of our socioeconomics here. Species that's near and dear to my heart, or a set of species anyway, Longfin and Shortfin squid. And I'm going to talk a little bit about these animals in the context of some of the research that we do and what we've learned about them. So by working collaboratively with the fishing community, this is from work we've done down in Nantucket Sound using commercial fish feeders, which are fixed in space and monitored daily over time. So it lets us get a really good record of the number of squid in these traps relative to water temperature. And what that does is it lets us model at a very high resolution sort of the optimal thermal habitat for these animals, their optimal range, where they perform best physiologically, undoubtedly influences their distribution. So looking at things like oxygen and water temperature and making some inference about what the best temperatures are for the species. And taking that information, you can in turn inform our understanding of when and where they're likely to go. So the idea that squid in particular are going to increase in the Gulf of Maine is based on the climate modeling and the increased temperature projections and knowledge like this of what sort of their optimal range are. Now, there is a point where they seem to get too hot as well, so that's something to consider. Seasonally, as they move, they may avoid areas that are too hot. But we're also noticing that, as you might expect, things like oxygen really play a role. So even if you have a good optimal temperature, the dissolved oxygen concentration can go down for a variety of reasons, not just temperature, and can cause them to shift their distribution as well. So this is the work that we've done with longfin squid, but I also want to point out that shortfin squid have been increasing in abundance in the Gulf of Maine as well. And this is from a couple of years ago now. This is from observations taken by both recreational and commercial fishermen. They were the first ones to notice that shortfin squid were really coming back in the Gulf of Maine. I should say squid are kind of interesting because they're kind of known for these episodic changes in abundance. They'll show up in big numbers for a couple of years and then kind of disappear again. But those sort of episodic events in the Gulf of Maine, especially for longfin squid, have persisted. So it's not just a thing that happens every once in a while. It seems to be happening more and more. And many of you who've been around Provincetown for a long time may have well noticed both longfin, but particularly these shortfin squid are known for stranding on the beaches. And some of you who've been here for a little while have seen that phenomenon in the past few years. That's arguably an indicator that there's more shortfin squid around overall. And again, it's taking an opportunity to point out that the fishermen's observations are really key to detecting these changes because they pick up on these observations long before our surveys do and things like that. Another species I want to talk about just briefly, we touched on that earlier, is black sea bass. Now, black sea bass is another one of those species like fluke that we consider sort of a southern species, but they're on the move. They're shifting their distribution north, and we're seeing them in lobster traps, in recreational fisheries. There's a variety of reasons why that can be both good or bad, depending on your perspective. First of all, they're voracious predators. They love to eat little lobster. On the other hand, they're also delicious to eat and also may be able to support a fishery in this area. And I just want to take an opportunity to highlight a monitoring project that we've been doing in Salt Pond in Eastham. It's a project that was started actually by a high school student from my alma mater at Nauset Regional High, Max Dio and myself, setting these traps around Nauset Marsh. Ultimately, we settled on Salt Pond for our long-term monitoring location. And this project has continued. Fred and AmeriCorps Cape Cod, where we go out and essentially monitor this trap at least once a week, one or more traps in this area. And one of the really neat things about the little traps that we use is they're perfect for catching black sea bass. So we're now starting to see a seasonal persistence of black sea bass throughout the year, and so far earlier every year on the eastern shore of the Cape. So I think with that, I just want to also highlight the importance of monitoring. Whether it's citizen science or more rigorous surveys or whatever the platform is, we really need to be paying attention to what's going on out there. The more we look, the more we see. And that's not just true of the biology, but circling back to what Sarah talked about at the beginning, thinking about the oceanography and the physical forcing and things like that. And again, this is a place where fishermen's observations become really important. We're part of a collaborative effort called EMOLT, Environmental Monitors on Lobster Traps. And it's been modified now, it's EMOLT squared. It's Environmental Monitors on Lobster Traps and Large Trawlers. Anyway, I love our acronyms in this world. But what this does, it gives us near real-time bottom temperatures around the Gulf of Maine and beyond. And that's really important. A lot of the oceanographic data that we get comes from either surface buoys or satellite-based instruments. But in this case, we're relying on bottom temperature, which is harder to get. Fishing gear, when you think about all the different types of fishing gear that go down to the ocean floor, spend a lot of time down at the bottom. So we're working to instrument fishing gear, working with the fishing community, and fishermen like to know what's going on down there as well. So through Jim Manning and his group, through EMOLT, we've now have this network of fishing vessels that are collecting data. Anytime their gear comes up to the rail of the boat and it's got an instrument on board, it sends a signal to a little box in the wheelhouse, sends a signal up to a satellite, and we get the temperature sometimes minutes after that gear is on the boat. And that can often be a long-term record depending on how long that fishing gear has been down the bottom. So this is a really good way to add critical data to that process. All the models that we talked about today really rely on good data. Models are garbage in, garbage out. And as we get more things like bottom temperature, which is tough to get, we can really refine those models and make better projections as far as the oceanographic change, things like that. I think I'm going to close right here. I'm being mindful of the clock here. And I think with that, I just want to take a moment to thank everyone for being here today. And I want to, this is meant for this evening's talk, but I do want to mention, I had something more thoughtful to say that I'll say tonight about this quote, but one of the last things Matthew said to this group was, it ain't what it used to was. And just talking about changes in the ocean. Oh, geez, you guys. Miss Matthew. Anyways, Matthew was commenting on the changes in our ecology during one of our evening lectures. I'm going to do this tonight, but I will not start it. Thank you very much. Matthew's been around a lot longer, been around a lot longer than we had. Really was a keen naturalist and observer of ocean change. And, change is the only constant here. And I think I'll stop right there because now I have feelings. Thank you very much.